Well, hi there. We're going to begin our Calculus 2 course with word problems. We're going to be discussing the relationship between velocity and distance and displacement. And then we're going to move that towards fluid flow and population growth and some cost and profit analysis as well as some consumption of natural resources. I'm Rebecca Weaver and we're getting ready to start this Calculus 2 course. You'll notice that I have some instructor notes in the Blackboard course for you. I expect for you to print those out. They go along with my video. If you'll print those out and make notes as you go, it will be a good guideline for what's going to be on your test, and they can be notes that you use while you're taking your tests. Okay, nothing really new here. We're just kind of formalizing what we already know about displacement and distance. So just going back over that again, displacement has direction. If what we're going to go ahead and say is if we're traveling towards the right, then our displacement, we will take that, whatever that value is at B and at A, and that value would be positive. So we're going to say that's positive displacement. If we're traveling in the other direction and the B is more towards on the left of the A, then we would say that we are traveling in we have a negative displacement. And following from that, if I take the integral of the velocity and find that area, the area under the curve above would be positive and below would be negative. Distance, however, and displacement is how far away you are from your starting point, whereas distance is just give me the total distance that I traveled, kind of like your Fitbit or your data on your step. It doesn't really tell you, if you start out and you walk several miles and then you come back home, your displacement would be 0, but you would still have traveled a distance. And so what we have to do in order to get that is we will have to break that into pieces. We're going to integrate it, say from, what we'll end up doing is we'll integrate it from A to this value and then from this value to B, and that'll be how we'll split it up for the absolute value. So don't get hung up on the absolute value. It's not like it's going to make it tough. We just split up the integral. So just formalizing our definition, where position is just where your location is. Velocity has to do with your distance over time, and it is the derivative of that displacement formula or your position formula. Displacement is how far away you are from your starting spot, and we can find that by taking the integral of the velocity and then distance, that absolute value, same thing but the absolute value, just so that we can make sure everything has a positive area, and that's what's meant by that. For our example 1, they want us to we have a cyclist that's pedaling with a certain velocity here over a time frame. We're supposed to graph that function from 0 to 3 and determine when that cyclist moves in the positive direction. So I'm going to plug that into my calculator and get that. Okay, there's my calculator result. Now they want me to determine when the cyclist is moving in the positive direction. Well, I graphed this from 0 to 3 like they asked me to. This is a 2, that's a 1, there's 0, and then this scale goes from 0 to 10 to -5, just so that you'll know kind of what's going on here. And this is my velocity, so we'll call that v of t, and this is my t. Alright, determine when the cyclist is moving in the positive direction. Well, that's when the velocity is positive, so it's in the positive direction. So I'll just write positive direction. Direction from, that would be from 0 to 1. And then in the negative direction, from 1 to 3. And notice this negative direction at the 1 and the 3, there's 0. So I'll use particular inequality symbols there. Alright, to find the displacement. Okay, displacement, here she is right here. Find the displacement at those particular intervals. So I'm going to find the displacement from from 0 to 1. That's going to be the integral of 1 of my 2t squared minus 8t plus 6dt. And I'm going to write that down for all of these and do those integrals. Okay, so I have them written down for you, so I'm going to do the integral, just reminding you this is going to be 2t cubed over 3. Remember, I'm going backwards from the derivative. 8t squared, I need that 2 in there and need the 3 because they weren't necessarily sitting there, and that's 6t squared. Oh, not sorry, squared, just a t. There you go. Evaluated from 1 to 0. I'm going to plug in the 1, subtract off plugging in the 0, and get that answer. And that would be, for this one, would be 8/3. And doing the same procedure for the 1 to 3, I would get a negative 8/3. So the area under this curve is 8/3. The area under this curve is 8/3. From 0 to 3, if I plug that in and plug in the 0 and plug in the 3, what I'll end up with is 0. Because the displacement is 0, that means that I actually am back at my starting spot. So then the next thing we're going to do is we're going to set up the distance. The distance is going to be the absolute value. So what I'm going to end up with is I can break this up because I want this section here to flop up on top. Then what I'm going to do is just make sure that that is going to be a positive answer. So I've written out the integrals. What I would need to do to get that absolute value is I just break it into two pieces. Here's the positive piece, and then the negative piece, I just, in order to flop it up, I just multiply it by a -1. So it's going to end up, because I already did those integrals, 8/3 plus 8/3, and this is going to end up being 16/3, and that's going to be my total distance. So let's look at that result on the graph. And this is exactly what we just did. We just found the displacement here for this section, found the displacement for this section, and for total distance you just make sure that you are calculating everything as a positive. For our next problem, what we're doing is we're taking this block and we're pulling it down and we're watching it spring up and back and up and back. You can watch the animation in the chapter contents if you would like to watch it move up and down and up and down. So initially the block hangs at rest. At T0 the block's pulled downward, so it's pulled here, and then we let it go, so it's pulled down. The spring is going to pull it up by virtue of the mechanics, and then we've got a function that relates that. So that function for that speed of that block, or that velocity, is that right there. I'm going to graph that on my calculator so I can look and see what's happening. Alright, so I've graphed my velocity function. This is v of t, this is time in this direction here, and I set my parameters so that it would graph it on the pies. I just set my window. You can do that just by hitting window and then hitting your X scale, and of course I adjust my window to fit how I want it to. Here's my initial position. That's something that I'm going to need when I go to find this position function that they're asking me to find. So up here, S of t is going to be the initial position, and the initial position, they've told me this S of 0 is -1/4 plus the integral of, and this is 0 to t, and my velocity function is 1/4 sine of t dt. I'm going to integrate that, and I will get -1/4 plus, and then I'll get -1/4 cosine t. This is then evaluated from t to 0. So plugging those in, I end up with -1/4 plus -1/4 cosine t minus, plugging in that 0 where there's a t, I'll get 1/4 cosine of 0. This is a 1. So that's going to give me a -1. Oh, that's supposed to be minus. I was like, where is that? Somehow my sign got dropped. There you go. So -1/4 plus -1/4 cosine t. That minus minus then becomes a plus, and I end up with -1/4 cosine, fix that, cosine t. And that is your position function. So I'm going to graph that with my calculator. Alright, so I've graphed the position function for you and set the parameters, and we see that at time 0 the block is at its lowest point, and we let go of the block and the block moves up. It goes back to that 0, that resting position where it was just sitting there before, and then it goes up, and you'll notice it goes up and it compresses the spring, at which point then gravity pulls it back down. It goes back through its position and back down to where we had originally pulled it from. Let's see what the velocity is doing at that time. The velocity is positive, and the velocity is speeding up. Now once it hits the origin, alright, once it hits the 0 position, the velocity starts slowing down. It's still positive, it's still going up, but it's slowing down. That's why these values are decreasing. At which point it hits the top, which is pi, hits the top up here at pi, and then the velocity starts increasing in the negative direction. And then when it reaches the bottom, then, or goes through the, this is where it goes through its little spot, and then it starts slowing down again, and here's where it reaches the bottom again. And you can see that corresponding over here on the position function. Got to remember which graph I'm looking at to see what's going on. So these positions correspond to where it is. Let's see. I think I marked that one. That's not 2 pi there. This one, right? Yeah. Oh, that's there. I fixed my axis here. So it's corresponding to where it is. Notice that at 0 the position is at its, at 0 at pi, it's at its highest point here, and the velocity is where it crosses over from being positive, meaning that it was going up, and now it starts going down. So when does a block move through the origin for the first time? Just look at the position function for that and find out where it was 0. That would be right here at the answer to C is at pi over 2. When does a block reach its highest point for the first time? Just look at the position function for that. That would be right here. That's when its position is the highest, and that would be the answer to D is at X, we'll just say T equals pi. When does the block return to its lowest point? It goes back to the lowest point right here. This is the other answer to D, and that would be at t equal to 2 pi. And I think we've answered that one. So just like I had to be very careful about which graph it is you're looking at and try to understand the relationship between these position graphs and the velocity graph, and be sure you know which one you're looking at or you'll get confused. Okay, trying to figure out this problem is kind of the hardest, but the graph really helps a lot. Here's the velocity function for 19 seconds. Our velocity is 80, and then from 19 to 21 we've opened up the chute, which means our velocity has then decreased quite a bit according to this linear function here, and afterwards our velocity is at 6 for the remainder until we hit the ground. And we would like to know the altitude from which he jumped, so we want to know our original position. So in order to find our original position, that means I would like to know the distance. And if I would like to know the distance, I'm going to use the distance formula for each of these little chunks, because each of these little chunks happen. So I'm going to set up my integral and then integrate. So you'll see that I just took each of those little chunks and their time periods, and all those answers are positive anyway, so I don't have to worry about my absolute value on these, and they're all going to be above the area above that curve. So I'm going to integrate these and get my answer. Alright, there's my set of integrals all set up, and then the last thing is just to chunk it into the calculator, and when I do, I get that oops, that shouldn't be a V, that should be an S. That total distance is going to be 1720. I believe we are in, we're in meters. Okay, there you go, that many meters above the ground. So this problem lets me realize that I don't just need displacement, sometimes I need total distance, and I need to look to see if things are above the axis or below the axis, so that I can get that positive area. Here we have a similar formula for velocity and acceleration relationship, so that I can get this velocity formula given an acceleration formula. And for this one, on the Earth we have a constant acceleration of the 9.8 meters per second squared. So that's not going to change. I will just go ahead and say that A equals 9.8. And that is, and it's negative because it's going to be pulling downward, so I'm going to plop that negative in there. And it looks like I'm initially shooting an artillery shell. Here's my initial velocity, so my V0 at time 0 is going to be 300, and my S of 0 is going to be 30 because I'm shooting it, that's the position at time 0. Alright, so I'm just going to plug this into my velocity formula here. V of 0 is 300 plus integral of t0, my A of t is this negative 9.8 dt, and that will give me V of t equals 300 plus, and I'll get that done for you. Alright, pretty simple one. I integrate that. It's negative 9.8t. I evaluate from t to 0, plugged in a t, got this, and when I plug in a 0, of course I get 0 for that. So there is my velocity formula. I could get my position formula because they did give me this. They didn't ask for it, so I'm not doing it. We're moving this forward into cell growth. Key here is to know that at time 0 I have 100 cells. That would mean n of 0 equals 100 number of cells. I'm just going to plug this into this future value formula here and integrate. Okay, you can see that I've set up my integral just like my theorem for net change, and next thing is to integrate and get my equation, and that's all they want me to find. Alright, I integrated and I used these points from t to 0 and did my subtraction, and when I simplified, this was my equation. This next example is a cost example. So we're looking at the cost from producing the 15 thousandths book to the 12,000th book. So I'm going to integrate this thing from 12,000 to 15,000, and they give me the formula. It is 12 minus 0.002x dx, and what I'm going to do is integrate and crunch these numbers. Okay, there's my integral after I've evaluated, and I'm going to punch in the numbers, and what I get for these numbers, 27,900, and that's the answer to the last one. And that concludes section 6.1. And if you have any questions with this, you can visit me on the Collaborate or email me, and I'll be happy to help you. It'll work best if you will send me some pictures of your work, and then I'll write on it and I can help you move forward from there. But if you have no clue, just let me know that too. Alright, and good luck.